Lecture 12 is the last serious examinable lecture in my half of the course, and what we're going to do today is look at the uncertainty principle. There will be one more optional lecture that will follow this with lecture 13, which will be a little bit of a sort of a fun look at quantum computing just to satisfy some curiosity. Where I want to go today is pick up the threads that we've been working on so far in this fourth week of the course. In lecture 10, you'll remember that we looked at simultaneous observables and arrived at the idea that if we have two observables and we want to be able to measure them simultaneously with accuracy, what we need is for their corresponding operators to commute. And that led us to something that we call a commutator, and whether or not that commutator is equal to 0 tells us something about our ability to simultaneously measure those two observables with accuracy. Then in lecture 11, we actually took a little bit of a separate position and just looked at defining uncertainty in a sensible way for quantum mechanical quantities. And where we arrived at was this idea that we can connect the uncertainty delta L to the expectation value for any given operator L, and have some sort of underpinning statistical idea of what uncertainty really is. Where I want to go today is to bring those pieces together. I want to take the idea of uncertainty and its connection to expectation value and commutators and join them together in two steps. The first step, which we'll do in the first half, is we need one more mathematical piece, and it basically comes from length being a well-behaved concept in the vector spaces that we're dealing with for quantum mechanics. Ultimately, the uncertainty principle really arises from nothing more than the requirement that certain length relations hold in our vector space. That'll get us to something we call the Cauchy-Schwarz inequality. And then in the second half, what I want to do is take all of those pieces, including the Cauchy-Schwarz inequality, build them together into what we call the general uncertainty principle. So basically an uncertainty principle for any two observables that we like, L and M, that we can then connect back to commutators, which we had in lecture 10. And then as a final example there, what we'll do is pick up the case of momentum and position and get back the classic Heisenberg uncertainty relation that you'll be familiar with from your first year courses as an example. So let's bring up some slides. Where we need to start is with something called the triangle inequality. And so you'll remember from vector addition, what we can do is take two vectors, A and B, and add them together to get a third vector, C. And when we do this addition, basically what we have is a vector A, a vector B, and the vector C basically points from the beginning point of vector A to the end point of vector B, okay? What happens here is these three vectors form a triangle, and when they form a triangle, there's one thing that we know geometrically about the lengths of the edges of a triangle. If you take the length of the hypotenuse, the longest edge, and add it to the length of the shortest edge, it's always going to be longer than the third side in the triangle, okay? It's something you may be familiar with from high school and hopefully have proven in your geometry classes. If you haven't, you've probably also seen it at university when you do vector spaces. And it's relatively easy to verify for yourself, just drawing triangles and checking the numbers. It should be fairly easy to prove as well. I'm not going to do it here. I'm going to leave it as a taken result that we know that this is the case. Where we start with this is we go from triangle inequality, basically the idea that lengths are sensible and geometry is sensible in vector spaces, and extend this thing to something that we call the Cauchy-Schwarz inequality, which is really just the same inequality in a slightly different form. The way I'm going to come down this road is I'm going to take the path twice. I'm going to do it the first time just considering real vector spaces so that I can take the easy way to getting to what I'm going to call my Cauchy-Schwarz inequality. Then what I'm going to do is I'm going to track back down that same line of maths, this time dealing with the idea that I've got a complex vector space, so I need to worry about conjugates, and also building in the notation that I have for quantum mechanics so that I end up with a form of this Cauchy-Schwarz inequality that is pretty much you can just drop all your quantum mechanical notation into and move on in the second half of the lecture. Okay, so to come down this road, I'm going to need some paper. And where we're going to start is just with the idea that if we take some vector A and add it to some vector B, we get some vector C, okay? Add together in a triangle. And we know that the length of the side C is going to be less than the sum of the other two lengths. So let's do this. The length of vector A plus the length of vector B is going to be greater than or equal to the length of C, and we know that C is A plus B. So really what we're looking for is the length of A vector plus B vector here. Okay. Now, what we're going to see in this lecture is that the inequality sign here, the greater than or equal to, actually gives us a little bit more freedom than we would have in equality, right? When you deal with equalities, you've got to make sure that the two terms on the either side are precisely equal. When you're dealing with inequalities, all you really care about is that what the side that's larger stays larger than the other one. And so often you can take little shortcuts here where you know that the thing on the right is smaller than, and you can replace it with something that's even smaller than, and that inequality will still hold. Okay, and we're going to play this game a couple of times as we go along through here. So first step here is we take the equation that we've just got and we square it on both sides. So we would have A plus B squared is greater than or equal to A plus B squared. Okay, so what we've done is just gone, this is bigger than this. If I square both, the bigger one will be bigger once I square it. Okay, if you imagine, say, 2 is greater than 1, then square both sides, 4 is definitely bigger than 1. We can then expand out this square here. Okay, so if we take this term on the left-hand side, we're going to get the length of A squared plus 2 times the length of A times the length of B plus the length of B squared. And that's going to be greater than or equal to, let's keep this term on the right-hand side here, like so. Okay, there's one intermediate step that comes in here, and that is that we can actually come sort of upper level in terms of the term on the right-hand side. Something that we know is if we take the dot product of A plus B with itself, right? So we're basically taking the dot product of C and C. This vector will be equal to the product of the two lengths, right? So A plus B, and the cos of the angle in between. And of course, because it's the same vector, that angle in between is 0 degrees, right? So this is cos of 0 degrees. Cos of 0 degrees is 1. And so this thing is basically A plus B absolute value squared, okay? So what I can do is take my term on the end now, and instead of having it as the square of the length, I can just take it as the dot product of that vector with itself, right? So what we've got here is the length of A squared plus 2AB plus B squared is greater than or equal to A plus B dot A plus B. Okay. All right. Now, something I can do with that dot product on the end is I can actually expand that as a sort of a multiplication, right? So this thing is going to be greater than or equal to A dot A, and of course A dot A, those two vectors are parallel to each other. So what I would have here is just the length of A times the length of A times the cos of 0 is 1. So it will be the length of A squared. I've got two A times B terms, which I'll put on the end, and then I've got B dot B, right? And B dot B, of course, is going to be the length of B times the length of B times cos of 0, because they're the same vector, is going to be the length of B squared. So this will be length of B squared plus the cross terms, and so they will be 2A dot B, right? Because there's two of them. There's A dot B and B dot A. And we're just multiplying vectors here, and you know that dot products, it doesn't matter which way around you do the dot product, you get the same answer. Okay, so this will be A dot B. Okay, so at this point, we can call this equation 1. What we can do is take equation 1 and subtract the length of A squared plus the length of B squared from each side. Because you'll notice that we've got these terms on both sides, and we can just subtract them off and get rid of them, okay? So our equation 1 here now becomes 2 length of A, length of B is greater than or equal to 2 times the dot product of A and B. And then, of course, the 2 out the front can go as well. I can divide both sides by 2. And so what I'll have here is the length of A times the length of B is greater than or equal to A dot B. Okay, and we know this is definitely going to be the case. Let's think about this for a second, right? If you take A dot B, what you're doing is you've got the length of A times the length of B times the cos of the angle in between. The cos function always runs from 1 through towards 0 and then out towards -1. It's never greater than 1, right? Which means it's absolutely impossible for A dot B to ever be bigger than the product of the lengths of the 2 vectors A and B, okay? So this inequality just makes complete sense. And you could almost say we could start from it as a starting position if we wanted to, but ultimately the triangle inequality is sort of often a nicer place to do it because it's the more obvious place for that to hold. Okay, so let's call this equation 2 for the moment, just to keep track of it. What we can do is actually square both sides of this thing again, right? And so now what we would have is square both sides. We would have square of the length of A times the square of the length of B is greater than or equal to A dot B squared. And of course, we know that the biggest value we can have for A dot B squared will be the length of A dot B squared in there because of the way the cos function works. So here I'm actually exploiting the fact that I've got an inequality here to basically replace something with something else that I know is going to behave in the same way. So what I'd have here is just length A dot length B squared. Okay, because I know that if I take that product, I'm going to have a cos in there. Cos will never be bigger than 1. This thing that we've got up here is what we know as properly as the Cauchy-Schwarz inequality. Okay. Like so. Okay. And that's how you'll mostly see it written. And it's really just an extension result from triangle inequality in a form that's kind of useful for us. So that's our end result, but in the form that it's written on the page there, it's not enormously useful for us to just drop our quantum mechanics into that. So what we're going to do is we're going to trawl back through that same line of algebra that we just did, but this time we're actually going to consider our vectors to be, rather than just real vectors on a page making a triangle, to be vectors in our complex vector space, and basically rely on, at that point, no longer having to think about it sort of geometrically and visualize it, but just we're going to abstract our way now down through a complex vector space to get the same result. Okay, so let's take the argument here that now our 2 vectors A and B are basically just kets, right? What we can do is get the lengths of those 2 vectors. So the length of A, let me just write this a little more cleanly. the length of A is going to be the square root of the inner product of A with itself. You remember this as the way that we normalize vectors. Then vector B is length of B is going to be the same thing. It's the square root of the inner product of B with itself as well. Okay. And then we remember we had a vector C, and it was really just A plus B, right? So we can work out what the length of A plus B is going to be, and it will have a very similar form. It's going to be the square root of the inner product that looks like this. So bra of A plus bra of B times ket A plus, hang on, let's get my notation right here, ket A plus ket B, like so. Okay, and so this thing will just multiply up in 4 terms. We take the square root, we get the length. Okay, now we're just going to follow down the exact same set of steps that we had earlier. So our starting position here will be that the length of A plus the length of B is going to be greater than or equal to the length of the sum of those two vectors. Okay, so length of A plus B. Exact same position that I started all the way back up here with. Okay. So we'll troll through just a little bit faster this time. We're going to square both sides, same as we did before. So A plus B, length of B squared will be greater than or equal to the length of A plus B squared. And again, we can multiply out those products, right? So what we're going to have on the left-hand side is the length of A squared plus the length of B squared plus 2 length of A, length of B is going to be greater than or equal to the length of A plus B times the length of A plus B. And on the right-hand side, we can do a little bit more simplification for this, right? And what I'm going to do is pull my inequality symbol over to the left so I've got a little bit more room. We can write this thing as the length of the product in here. So this is going to be bra A plus bra B, ket A plus ket B. And so you can see already what we're doing here is more or less treating these things this time, rather than just being real vectors, as complex vectors where we need to start caring about the conjugates properly, okay? So now when we do this multiplication of the lengths, we can get 4 terms in here. So this will be greater than or equal to the length of something that's made up of a whole pile of inner products. A with A, B with B, A with B, and B with A, like so. And then the last step here is basically just to treat the length of a sum of inner products as a bunch of sums of either lengths or still with inner products in here. So what we can do is write this thing. Let me just add one step in here. This would be the absolute value of A plus absolute value of B. Whoops, hang on a second. I need to get rid of that. Plus, and we can keep these last 2 terms inside the common absolute value here. Let's get this. A, B, oh, come on. AB plus BA. Like so. Cool. And then we know up here that the square root of that inner product is just A. So if we take a square just to get the inner product A times A, then we will get the length of A squared, okay? So what we can do is replace this thing with length of A squared plus length of B squared plus absolute value A, B plus BA. Like so, okay? Again, we can take this same trick that we did before, which is that we've got an a squared and a b squared and an a squared and a b squared on the two sides, right? So you remember we subtract that off. Length of a squared plus length of b squared from both sides. And so that will get us what's remaining, which is 2ab is greater than or equal to a, b plus inner product of b and a, like so. And this is also something that's basically the Cauchy-Schwarz inequality as well. Let me number it equation 4 and just clean up this absolute value sign over here, just so it's nice and clean. It's basically another form of Cauchy-Schwarz inequality. You can write whole piles of different forms of it, trying to get to something that you really want. But let's take one last step with this thing, which is to write it in its most common form as it gets used in quantum mechanics. So one more step we can take in here is we can basically write these two lengths just up on this line here as inner products as well, right? So this will be the square root of a and a times the square root of inner product of b and b is greater than or equal to ab plus BA. And then what we can do is, again, we can square both sides, right? And so now you probably see why, if we go back up here, you'll remember right after getting equation 2, I squared both sides again. And it seemed like, why would you square both sides again? You've already kind of got something nice. And then we end up with this funny Cauchy-Schwarz inequality in 3 that kind of, you go, well, why do we have the squares on there? The one that we had back up at 2 was a lot more meaningful. The main reason why we did that is because now we're going to follow the same path and it's going to take us somewhere useful this time. Okay, so we're going to square both sides. So if we do that, 2 by 2 is 4, so that gets us a 4. The square gets rid of the square root around the inner product for a, so this is now just a inner product of a and a. Same thing happens for the b. We get rid of the square root there, so that's now b and b is greater than or equal to what's going to be the square on the right-hand side. So the square on the right-hand side will now be a, b, hang on, let me just get the angle bracket there, ab plus b, a times a, b plus b, a, like so, okay? And so what we can do now is the same idea. We can take the length of the sum is equal to the sum of the lengths, right? So this thing would be now a product in here. Let me take the inequality sign over. It's going to be the product of length of a, b plus length of b, a. And of course, these inner products are just numbers, right? So really all I'm doing at this point is just taking an absolute value times the same thing. Oh, hang on, I've lost my left bracket. And this is a habit you get into when you do enough of these problems as well, is spotting when you're sort of dropping out brackets in notations and not keeping track of yourself. And it's even more challenging if you're trying to talk at the same time. Okay, like so. Quick check, everything's right in that line. Okay, so then we can just basically multiply this out, right? So this is going to be greater than or equal to inner product of A and B times inner product of A and B plus absolute value of A and B and B and A plus another one here, which will be B and A and A and B, and one more, which will be inner product of B and A and B and A again. Okay, I'll let you work through these all for yourself more slowly later on and double check that everything adds up in your head. Now, really what we're doing here is taking products of inner products, right? And so we know that inner products really are just you take two vectors, you take the dot product, and it doesn't matter which way round you do it. And if you take the absolute value of that thing, or you take the length of that thing, absolute value and length are more or less the same thing. You basically end up just with a number. So all of these four terms that we have in this line are actually the same thing, right? What this is really saying is that it's greater than or equal to 4 times A, B, A, B, because we could write any of those either way around. It doesn't really matter, so we can collapse that term. And we could put this thing just as AB squared, okay? And so then we end up with what is our final form for our Cauchy-Schwarz inequality. And we're basically now at the end of the first half of this lecture, which is the inner product A times the inner product B is greater than or equal to 4 times AB squared. And of course, you remember this idea with the inequality, we can always replace it with something smaller. So this thing is always going to be greater than or equal to just AB squared, okay? So what we're saying is the inner product of A with itself times the inner product of B with itself is always going to be greater than the square of the inner product of A and B. Really useful relation, and this is our Cauchy-Schwarz inequality. Like so. Okay, so depending on what book you're looking at, you might see two forms for this. You might see this form that we've got written at the bottom here, which is basically the equivalent of our equation 4 back up here. Or the preferred way I like to see it, because it's actually more useful for getting out uncertainty principles, is what you'll see just up here, which is sort of our final equation down there. Let's call it 5. Oops, wrong color. So with that, let's take a quick break. You might want to go away and have a look and double check through the maths and make sure you convince yourself that you're happy enough with that inequality. And then what we'll do in the second half is we'll use that inequality to get ourselves an uncertainty relation. I'll see you then.